Samsung just right. It's just your phone sitting on the journal.
Yeah.
Yes. Good question.
I don't know. That's what research is.
Okay guys, this is Digital Electronics Lab. I'm going to take the roll really quick and check your homework. Get out the quiz and we'll go over it as soon as we get done with the homework. Or the quiz review, sorry, quiz review. Corey?
I only have half the homework because I've got to do tomorrow and finish it up. So
Okay. Okay, thanks. Ben? Ben's not here today? It's not good. James? Alright. Cool, thanks.
That
Any problems with it?
224, I didn't understand how to do it.
Okay. We're going to go over that today too as well. Thanks. Dakota?
Those ones tonight. I
Okay.
didn't get the second section. I didn't understand that one. And
Okay.
I was,
Alright, we'll go over that. Thanks. Jesse?
that's where we started at.
Okay. Put your notes right there.
yes,
And then that's part of your homework.
yes.
And then those two, or that's just practice?
Yeah, that's just more notes and stuff.
Okay. Okay, thanks. San Juan? Christopher?
.13 to 2.31.
Good. Okay, good job. Leon? Okay, good job. Jason? Austin? Okay, you can still do the homework. It's on Moodle. You can get half credit for turning in tomorrow.
Is there anything else on
talk to the guy right next to you. What did he miss? Probably a handout on the quiz that we're going to go over today. Gary? Okay, 31. Okay.
This is a Friday.
Okay. Good job. Lucas? Okay, good job. All right, thanks. Don? Okay, good. Kevin? Okay, good, good. Tyler? No homework? Clarence? Okay, thanks. Okay, good. We're going to go over those today. A couple of comments before we get started. One, as I was writing down who did their homework today in my grade book, I noticed that with the exception of one person, everyone who did their homework and completed it got an A on the last quiz. Something to think about. And I'm talking about everyone who did the homework and completed every bit of them, all of them. So there's a very strong correlation between people who make good grades and people who do their homework. Another comment is if you miss class for any reason, go to your classmates and ask them what you missed, or go to Moodle, okay, before you come to me. It's okay if you come to me if you do the first two things first. Go to your classmates, ask them what you missed, and go to Moodle and see what you missed. And if you still are lost and someone's not able to help you, then come to me, okay? That encourages collaboration, and that's what employers want to see. And that's what you're going to do if you're working at a job. You're going to go to your employees, so we want to encourage that. Okay. So here's a very good example of what the quiz is going to look like. Okay, so that quiz is going to be on Wednesday. So describe the conditions with which the AND gate has a logic 1 on its output. Anybody want to work on that one?
All inputs are high.
All inputs are high.
Can I make it on time?
Yeah.
Did
You want to show me?
homework?
You can show me the homework after class. Just come up and make sure I mark you and get your homework at the end of class. So Clarence said when all the inputs A and B are 1, right? Who agrees with that? Everyone? Okay. Good. Label the inputs of the gate below with the correct logic value such that the output Y is equal to 1. What would that be?
A0, B1.
A is 0, B is 1. Is that true? Who agrees with that? Actually, there's a lot of. What's another choice?
If there's any high on the inputs, the output will be high.
Yeah, any one on there will be. It could be 1 0, 0 1, 1 1. any of those? This says to draw and describe and draw how we would use an OR gate to inhibit a clock signal. Okay? So I'll just draw that since it's going to be hard to... Oh! I need to get a different pen here. Okay. We just need to have a clock. Okay. Okay, if we want to clock out, what logic level will we put on the other input? Zero. Why zero?
Read one or the other. Have them both at one, somebody zero. Both zero.
So what happens if we have a 1 here?
That should be a zero coming out of the left on the clock.
Should be a constant one.
Yeah, if we have a 1 on the input here, then we're going to have always a 1. Doesn't matter what's on this input. Okay, so you're always going to have a logic 1. So that's why you want to have a 0 to inhibit the signal. Or a 0 to pass the signal, a 1 to inhibit the signal. So the 1 will always make the output 1, which inhibits the signal. Inhibit means to prevent or counteract. So a 1 inhibits the signal. A 0 will let the clock pass. Okay. Convert the binary number 1001 0110. Convert that to hex. You guys go ahead and try it on your papers right now.
96.
96? Does 96 exist in hex?
96.
Yeah. 96 doesn't exist in hex. Yeah. Let me turn on the light for you. What kind of work do you have? Oh, okay. How about work on the second one too? Convert the hexadecimal number 3C0D to binary. Are you good on the first one? 90. You can put a little spacer. Now, when I write these numbers, usually I put a little spacer, like a little underline. So if I was going to write 3, let's say I was going to start right here, 3, I would go 0, 0, this is 2, that's a 1, so that's, now we hit a little space there. And then I go on to write the next one. who's having a problem with the C? Anyone have a problem with the C? The C, is anyone having a problem figuring out the binary equivalent for the C there? You think it is? Okay. I always write it down. 1. So the way we do it, the way I do it, is I say, okay, I know this is 9. A, B. So this 9 is easy to remember because you know that this position here, 8. And this is 1. So you know that's 9. And then you just start adding 1 to each one. You got A, B, C. You go to D. 1, 1, 0, 1. Everybody good with that? Anyone have any problems? Is there any questions? Good. So everyone's going to make an A on this part on the quiz. Good. Some people were just afraid to ask, so that's why I'm worried. Are you good? No? Okay, so all you do right here is you just take 3 right here, and you put 0, 0, 1, 1. Put a little space there. Put a C, and then go find C. But now on the quiz, you're not going to be given this table. You're going to have to be able to derive that table. 0, 0, 0, 0, 0.
D is 13.
Yeah, you guys aren't going to have anything for the quiz. You're going to have to be able to derive the table on page 15.
I always go from the right to the left to the right because we start out with 0. Just put a 0. 4 0 6.
Yep. Convert this number to hexadecimal. One thing you do is you just have to have this table here in your head, or you have to go just write it.
1, 2.
I don't have this in my head. What I just do is I just start.
Right.
I just start from 0 and just start counting. You know, just make the counter, and then make your hex numbers.
1, 2, 4, 8. Double these steps. 1, 2, 4, 8.
Let's see what. See, now that's the problem. I ask people if they don't have notes. They say, "Oh, I'm fine." No one's fine. People aren't fine. You have to say something in class, you know. You got it? Okay. So how do you do C right here? How do you do C? How do you convert that? Go to page, what is that page on the book?
Yeah, just right there. Hey, I just go A, B, C, D, E.
Page 15. You guys who are already done with this, you can continue on, going on, and we'll go over here in a minute. Yeah. What you do is you take this number, you say the C, a 3C0D. So quick what you do is you go 3, so you write down that binary number. No, a 0011. 0011.
Oh, I was
This one right here. You know what? Do you actually mind? Do you mind showing him? Like just to make sure that he actually writes it out. You know, he writes out the number on his own. Okay. So if the high time for a periodic signal is 5 milliseconds and the duty cycle is 60%, what is the period?
Let me guess. This is one I don't understand.
Okay,
8 milliseconds period.
8 milliseconds. Okay, well, I don't know the answer. Let's derive it. Let's see if we can derive it. Go ahead and use a piece of paper and see if you can derive the answer. The answer is not as important as how you get to the answer.
You went down by your guy, it's 96.
So what you're going to need is
Well, no, just instead of saying 96, you go 96.
So I still feel like that, but it's considered 9.
Yeah, you wanted to write it down so nobody can make a mistake on it. So you say 96H. That would say hexadecimal, or you would say 96 with a base of 16. And they would know it's hexadecimal. That's what you're
yes.
When I do the first one, it's done with 1, 2, 4, 8. After that, I can but I'm gonna have to do it.
Duty cycle.
Oh, you got enough fingers, all right on that one.
Time high over period. So what you can do is what's the period?
Signal. If you don't want your clock to go through, it's a high. Right. You make it a high.
Time high 5.
If both of these are high, the output's high. And what you want no low.
That's what he drew up.
If anything,
See what now you have this answer. Let's assume this is the answer.
So then we'd have to do that.
Period 8.33. So does this equation work now? Time high over 5 over that. 5 divided by 8. You think you should say that?
I put a 1
Yeah, you have to divide.
Well, it's still going to stay 1. Right? Put this in the state there.
Sure, I'll show everybody right here.
Clock.
Okay, everybody. If you look on page
Anytime.
19.
yeah, page 18, page 19. The duty cycle of a waveform is defined as the time that it's high over the period. What does that mean? Well, that means if you have a repeating waveform, this is called the period. Okay? And this is called TH, or time high. Okay? So the duty cycle is going to be, the time high divided by the period is going to be the percentage that it's going to be high, or the percentage that it's going to be on. So the duty cycle is always in a percent, or in other words, duty cycle is a number between 0 and 1. Or you can think of it like 0 to 100%. However you want to think about it. But when you do the math, it's always, the duty cycle is going to be in a 0 to 1. So normally the duty cycle is 0.8, 0.6, it's going to be point something. And for example, if it says 0.5, if the answer is 0.5, that means it's 50%. If it's 0.1, that means 10%. If it's 0.9, that means 90%. So let me just write that out. 0.1 for duty cycle means 10%. 0.5 means 50%. 0.8 means 80%. Okay? Now, the equation, duty cycle equals time high over period. How can we use that equation to solve this problem? It says if the time high is 5 milliseconds, okay, that's this, 5 milliseconds, and the duty cycle is 60, well, we're going to have to convert the duty cycle, we're going to have to get it out of percent to just a regular number. We can do math. Okay, so it's going to be 0.6, 0.6. That represents 60%. It says, what is the period? So you have an equation. This is arithmetic, okay? This is not algebra or something complicated. This is simple arithmetic. You have a number and you have equals to another number divided by another number. Okay, it's equality. So, how can we get the answer? What do we do?
Divide the time high by 0.6.
0.6.
The point.
Divide the what?
Time high.
By 0.6. Yeah. Divide the time high by 0.6. What you do is you have to flip these numbers here. Okay. You flip those two numbers in your equation, and it gives you time high over duty cycle equals period. Okay. So you divide the 5 milliseconds over the duty cycle of 0.6. That gives you 8.33 milliseconds. So what does that mean? What does that mean? That means that if you have a 5 millisecond signal and an 8.3 millisecond period, that will be equal to 60% duty cycle. And let's see if it works. Let's see if it works. So we're saying, let's say that this is 5 milliseconds. This is 8.3 milliseconds. The question is that 0.6? Okay. So we know the duty cycle is equal to time high over period. So that's going to be 5 milliseconds over 8.3 milliseconds. What happens if you divide those two numbers? It gives you 0.6, which is 60%.
So your number doesn't have to be an equal time cycle?
What's that?
Doesn't it have to be an equal time cycle?
The period does it have to be an equal number?
I mean, the time cycle, if each one of your highs are
to round it up and have.
Are you supposed to round it, or is it supposed to stay?
No. No, if you round 0.6, it'll go to 1. That makes 100% duty cycle. This number is not supposed to round either. It's 8.3. If you round it, you're going to lose a lot of your precision.
It's 8.3 with the line over it too, isn't it?
Yeah, it repeats. So it's 8 1/3. So what does this mean? This means that you're probably going to have to memorize this equation for the quiz and know how to use it. Memorize it and know how to use it.
Is that the work that you want to see? Like, because I kind of have a easier way that I remember it. Like I do two. Like you had time high over time as one, so you can put 5 as the time high over t, and then that equals 60% over 100%. Not really. Well, I mean that is, but go to the right and go equals 60 over 100.
60 over 100?
Well, I mean it's 60%.
Yeah, 60 over 100.
Of the duty
Yeah.
cycle. And so,
Yeah, it's the same thing.
you know what I mean?
Yeah.
Like, so I'll divide the 5 by 60 and then multiply it by 100.
Oh, it doesn't zoom for you guys. I can zoom on this thing, but it won't zoom up there. Okay. So what about this next one? It says, in figure 1.18, the fall time of this waveform is... Let's work on that. So if you guys can... You know what the fall time of this waveform is? Show me on your paper what it is. Okay. Mm-hmm.
All time is 10%. 10% for 9%. So 10% lines falling down. It's just determining how much, how long
It's defined in the
it
book
takes
as
to
being
fall.
90%
I'd
time
have
and
to
10%.
well, basically,
Right here.
time to get the time.
And then go down here. Tell me what value is that. Go down, straight down.
Just the ball. From there to there. One, two, three, four.
Okay, so what would be the answer? How would you?
A little over 4 microseconds. Yeah, the vision is just can't predict your microseconds on the time, just time seconds. You're asking about time, it's not asking about how long it's taking. So that's this one. Here, so this down here, from there.
Right here.
Oh, okay. Yeah, unless that's a multiplication, unless it's 15, 20, 25, 30, whatever divisions they are, you can file one, so it'd be times whatever the total seconds are.
You know where?
Yeah, I'm sorry, million to the second.
Basically.
Yeah, it's actually gonna be something like that. Time second equals. So you could say.
Okay, guys, so I'm going to just show everyone really quick on the board, hopefully. I know it's kind of small, but what you do is you take the 90% point right there. Notice that it's not at the top, all the way at the top, it's not all the way at the bottom. And you take the 10% point. And the reason we do this is because it may take a long time for a signal to fall. So we really want to capture the time that it's transitioning as best as we can. Now, you don't always have a graph that looks so nice like this one. It kind of gives these perfect little lines to show you where you're at. A lot of times you have to really search to find out where these points are at, but this one makes it pretty easy, this graph here. If you read from this, you go down, you're going to find this is 17 and a half, and then this one is 21 and a half. So what you have to do is you have to say 21 and a half minus 17 and a half. And then you have to remember that this is in what? Microseconds. This is milli, this is micro. Milli is what?
Thousands.
Yeah. Micro is what?
Millions.
A million. There's a big difference between milli and micro, and sometimes people get those, assume that they're synonymous, and they're not. You good with that?
Is that right?
Mm-hmm.
Okay.
Next one is list the hexadecimal numbers from F1 to 110. Just go ahead and do that on your paper right now. And go ahead and work the last problem. I just want to see what you come up with for the answer. Given that A is equal to 1, B is equal to 0, and C is equal to 1, determine what the output value for Y is on the NOR gate. Yeah, just go all the way down your page. F1. What's the next one? Or you can go across. F1. What's after F1? F2. I want to put a comma there. What's after F2? Yeah. Yeah, I'll skip number 8. You guys can work on number 8 too. Raise your hand if you have a question. Raise your hand if you're confused. If you cannot do the hexadecimal problem in order, raise your hand because I want to come help you. Can you do after F1? Huh? What's after F1? What's after F2? Go ahead and work on your. Raise your hand when you're ready. Well, he hasn't showed you
Right.
the results going to be
Start
that.
here, so you're starting at one, so it's just.
And then you have to multiply it by 16. You want it with the number that's a decimal point. Go ahead and do it on the
Yeah, because
calculator.
they started with a even, and then you have to go all the way through there.
And then what you're going to do is delete everything except for the
To
decimal.
get back to all the other two, and then go back to this, then try to get this one. But you got to do this, that was all along, I think I've given it, they.
There it is.
Oh, you're working on the last one? Yeah, that one, what's the number after F1? What's after F2? Yeah, what's after F9? Okay. Yeah, this one right here is 1, 0, 1. The output of the NOR gate, what do you think would be here? So if we have a 1, 0, 1, what would be the output for the buffer? 1, 0, 1, or let's just say that you look at the OR gate before the buffer. 1, 0, 1. OR gate works with, you only need 1, 1, you can do 1. And then when it gets inverted, you go to 0. Yeah. Really quickly, I'm just going to work on the OR gate problem, the NOR gate problem. If we have a 1 and a 0 and a 1, before the bubble, we only need 1 in order to get a 1 on the OR gate. So we have 2 1s. So we're going to get a 1 on the output of the OR gate, but then it's going to get inverted, and it's going to go to 0. Okay, so that's the easy way to do the NOR gate. What's the number after F1? Is F2. Okay, after that is F3. What comes after, and then it keeps going. What comes after F9?
FA.
FA.
Comes after
FB.
Yeah, 1, 0, 4.
Yeah, and then after FF, what happens is you get 1, 0, 0. Yeah. Because if you look at FF is really 1, 1, 1, 1, 1, 1, 1, 1 in binary, right? So if you add another 1, what's going to happen? You're going to have to wind up carrying all those. If you put in another Mankala bead here, you're going to see that it's going to have a domino effect. You're going to have to keep carrying until you get all the way over here. So the next number is going to be 1, 0, 0, 0, 0, 0, 0, 0, 0, which is 1, 0, 0 in hex. Yeah.
You gotta go to 1, 0, 0. And then after that, you go to 1, 0,
1, 0, 0, 1, 1.
It's a base of 16.
What's after
Base of 10.
1, 0, 1?
So you're looking at a base of, if you're looking at a base of 10, then you can go back, you're looking at a base of 16. So we're looking at a base of 16.
That's not like
If we're looking at a base of 2.
okay. What's after 1, 0, 1?
1, 0, 2.
Yeah, it's not. Someone put this. It's not binary. It's 1, 0, 2, 1, 0, 3, 1, 0, 4. It's hard to tell because you guys won't talk to me. I don't know if I can trust you when you guys say you're okay. Okay, well let's work on the homework.
Quiz Wednesday?
Yeah. Yep. You good? You feel comfortable? Oh, okay.
Well, I get cocky and then I
Yeah.
do stupid stuff.
What's the hardest thing about this quiz that you worked on? What do you think's the hardest?
Duty cycle.
Duty cycle?
Now it's not. But it was.
Okay. Well, you kind of have to remember an equation or memorize it, and that's not always easy to remember those things. Try to remember it in a way where that you can recall it later. I know that sometimes we get in the habit of memorizing things for quizzes and tests, but try to somehow store it away so that you don't forget it, because it's a very common type concept. For motor drivers, for example, most motor driver DC motors they're controlled by duty cycles.
That volume stuff kind of throws me a little bit.
This is your homework, right?
Yes.
213. Okay. Can somebody read 213 for me? I don't have my book with me.
Write a descriptive sentence for the operation of a 5-input NAND gate with inputs A, B, C, D, and E, and output Y.
5-input NAND gate, right?
Yeah.
Okay, so the answer is output Y is low if, let's say if, inputs A and B and C and D and E are all high. So, one, two, three, four, 5. It's a NAND gate. Okay. Output is low if. So the only way you're going to get this thing to be low is you have to think about it. The way I think about this is think about an AND gate followed by an inverter. The only way you can get this low is if this one is high, right? That's the best way to think about it. Right? So if this one has to be high, then since it's an AND gate, all of the inputs are going to have to be high. Is that simple?
Yeah.
Somebody's going to miss it on quiz.
Yeah.
Okay. 2.15 required gate is, okay, what is the question on 2.15?
Says a pump motor in an industrial plant will start only if the temperature and pressure of liquid in the tank exceed a certain level. temperature sensor and pressure sensor shown in figure 2.47 each produce a logic high if the measured quantities exceed this value. The logic circuit interface produces a high output to turn on the motor. Draw the symbol in the truth table of the gate that corresponds to the action of the logic circuit.
Okay. Well, this solution doesn't really have the logic table. So you have a level. You have some fluid in here, and you may have to read the problem to me again.
And it has to be heated to a certain point before it come on.
The level has to get to a certain point in order for it to turn on?
And the heat and level has got to be at a certain point.
Okay. So we have a level sensor, and you also have a temperature sensor in here. And when they get to a certain temperature and a certain level, they're both going to be logic 1, right?
Right.
And then what do they want to do with that?
They want to figure out what gauge you would need to turn the motor on with that.
Oh, to turn them to
Once they're both 1,
The 2 input and
what gate would you need to make a 1 output?
Oh, okay. Yep. Since they're both of 1, when it gets to this is the temp T, this is the level L. When it gets to that level, we have a 1 and a 1, so the AND gate will be a 1.
To turn on the motor.
Yeah. So it'll be an AND gate. How about 1-7? 1-7?
Draw the circuit of a 3-input NAND function made using only 2-input logics.
Okay. Well, you want the regular way to make if you only have 2 inputs, okay, the way you would make an AND, we'll do that one first, that's the simplest. The way you would string 2 input AND gates together to make a 3 input AND would be that logic. Okay? Now, if you want, instead of a 3 input AND, if you want an AND, then all you have to do is you have to remember to bubble the last gate. Okay? Any problems with that?
Well, not really. I just
Okay, let's look at it again.
misread it.
Okay.
Like I thought it was like we did in class, so I did it like that. That's the same thing, isn't it?
But they want a 3 input NAND, I think. Right? It says 3 input NAND.
Isn't that
This would be a 3 input AND.
really?
Yeah.
Well, okay.
Well, let me see it for a minute.
Would it? Because I put that.
Yeah. So this here. Oh, you're using all NAND gates.
And that works, right? But would that pass on a quiz or no?
It wouldn't work. So this wouldn't really work. It's because you got this extra bubble there. That's the problem. So that wouldn't really work because this bubble doesn't belong here. Okay. And plus, another problem is if you really want it to be an AND, then you don't need this gate. So let me just go over it again. You want a 3 input NAND. The best way, so you really what you want is this. 1, 2, 3. But the only thing you have is you have some 2 input AND gates and you have some 2 input NAND gates. Okay? These are in different packages. These are in different parts of the chip. So the way you wire this up is you take this, you connect here. You label this A, B, C. This would be Y. Okay? And the way it works is you got a 1, you got a 1, you got a 1. This 1 and 1 turns into a 1 here. And you have a 1, 1. And then those 1s turn into a 1 and then gets inverted to 0. So the only time you're going to get a 0 is when you have all 1s on the input, which is the same function. A, B, C, Y. So the only time you're going to get a 0 here is when you have all 1s on the input. Okay, how about, can someone read 19 for me?
Draw the circuit of a 3-input NOR function with only 2-input logic.
3-input NOR function with only 2 input logic. So you don't have 3 input. So what you want is this function, a 3-input NOR, but the only thing you have is, you have a bunch of OR gates and you have a bunch of NOR gates. That's all you've got. Remember, these are in different IC packages. So these would be in one type package, this would be in a different type package. So what they want you to do is, how you would wire this up is you would take this bit there, bring this pin out, this would be A, B, this would be C, and then this would be Y. These other gates over here, you don't need to use those. Okay? Just to draw it really simply again, one more time. Using 2-input logic, this makes you cascade an OR gate with another OR gate in this manner. The way you do it, you take the output here, you put it to the input of this one. That gives you now 3 inputs, because you have this additional input. Then, if you want an OR gate, you just call this Y. If you want a NOR gate, you put a bubble here, and you call this Y. So this will implement a 3-input NOR. Okay. What about 21? Someone want to read that one?
21 is show a circuit for a two-way switch for a stairwell. This is a common circuit that allows you to turn on the light from either the top or bottom of the stairwell and off at the other end. The circuit also allows anyone coming along after you to do the same thing, no matter which direction it's coming from.
Okay, so a 2-way switch, right? I mean,
in the field we call it a 3-way switch.
3-way switch. Yeah, we call it 3-way switch. That's right. 3-way switch. So you have a hallway, then you have a switch. In this case, they wanted to define both switches off as on, and if both switches are on, then it's on.
It says what logic function does this represent? And draw the truth table.
Yeah. So what if could it be represented by and?
Yes.
No.
No.
Yes, it can.
I got it down as an exclusive NOR.
That's
That's what the answer says in the back of the book, and it makes no sense to me whatsoever.
What's the answer about the book?
Exclusive norm.
Okay, would this work? This is an AND gate. Or let's just say that this is not really any gate. But let's say that we make this an AND gate.
You have to have 3 AND gates. Right?
Would that work?
You make it work with 3 AND gates. You make it work with 1.
Why would this not work? Or why would it work?
Because when both switches are in the ball, why it wouldn't work? Both switches in the off position or in the other position at the top, if we on the lights to be on. It would only be on from one direction in that respect.
Yeah, I guess you have to think of one person is A, one person is at one end of the hallway, this person's at the other end of the hallway. Would
But you have a A1 and an A2 and a B1 and a B2.
yeah. See, would this person be able to control the light? In other words, does the output follow what he's trying to make it do? Him toggling the switch doesn't always toggle the light, right? It would be some sort of a function in between that. He would get really frustrated. Okay, so let's go back. What about an OR gate? Would OR gate work? Think about person A, I guess, again. If he toggles this, if he turns the switch on, he goes 0 to 1, on, off, on. Is he going to get the output that he wants?
Not all the time.
No. See, this here is going to be controlled by B, so that's not going to work. Okay. Well, what could we try? Let's try an exclusive OR gate and see if that works. How does exclusive OR gate work?
0, 1, 1.
It's like an OR gate, but it excludes the case where you have both ones here. Okay. Well, let's see if that would work. Okay. A turns it off, A turns it on.
He's still controlling it, I think.
You think is that going to work? It's not going to work?
A doesn't always control. Twice he's on, and he's switched it on twice, and one time it's on, and another time it's off.
Yeah, but you have to think of it like this. Is A going to be able to get the light to turn on or off?
It's not going to follow what he does each time.
Well, it doesn't really. He doesn't care. I mean, it's not saying that when he turns the switch to position 0 that it's going to be on or off. It just tells him he's going to be able to toggle it. It doesn't say that he's going to be able to, the switch is down, so the light needs to be off. It's just saying he's going to have the ability to toggle it. Always to toggle it.
Does he?
But B is going to have the ability to toggle it as well.
So, yeah, it's not working the one way and he tried it the other way.
So let's say that the B guy has it. He has his switch in the 0 position. Is the A person going to be able to toggle the switch in this case? He's able to toggle the switch with the B person having it in a 0 position. So let's ask the next question. If the B person has it in the 1 position, is the A person going to be able to toggle the switch? Yes. So it doesn't give you a definite off or on, but it gives you the ability to toggle. You can always toggle. You always have control, but it's kind of frustrating because as soon as you turn it on, B could turn it off. But you still have the ability to toggle it. Both people have really equal ability. No one is the master in this case.
They
Yeah.
get the answer.
Don't we have, sorry, don't we have the same setup in this room? There's switches on both sides.
Yeah.
So one person over there, one person over here.
Mhm.
They gave the example, the answer is exclusive NOR.
Well, either one would work
One
because
would work if that's true.
all you have to do is if you invert this, does it take away the A's ability to toggle the switch? No, it just changes the polarity of it again. Really, exclusive or an exclusive NOR would work. Inverting the output doesn't have really any effect on this type of function. Okay, what about 22? Anyone want to read 22?
Did we do 22?
Yeah.
I thought we just did 21.
No, it's
23,
24.
24.
Oh, yeah.
What about 21? I thought we only did.
We just did 21.
Yeah, we
I
just
just
did
didn't think
21.
22 was part of our homework.
Yeah, I didn't go along, so.
Can somebody read 22?
It says find the truth table for the logic circuit shown below. It's two XOR gates and two input.
Oh, okay.
XOR gates.
So we have this. Okay. So the easiest way to do this problem is do them one at a time. So take the A and the B. And remember, exclusive OR gate is a difference comparator. That's the best way to think about it. And you're going to get you're going to get a 1 on the output when you have a difference on the inputs. When they're the same, you're going to get a 0. You're going to get zeros. So once you're able to generate this table, then you apply the same thing to these two inputs. Because if you think about it, this input now is A. Well, I need to change my color so I can see it. This now is A exclusive OR. Well, I ran out of drawing space. Let's go back. This input with the arrow on it is A exclusive OR B. So you can really connect it to this one. Okay? And then the C input is here. So now when you do your truth table, you want to see when do you have a difference here. Whenever you have a difference in numbers, you put a 1. Okay, we got a difference in a number, you put a 1. When they're the same, you leave it a 0. Okay, so we have difference in number 1, difference in number 1. That's the easiest thing about the exclusive OR gate is it's simply a difference comparator. Is that any problems with that one? It's a 2-step process. You generate A exclusive OR B first, this table. And then you use that column and the C column to produce your final output.
Would you use that in real life?
Well, let's look at it. You know, there's going to be, when we start getting into more digital design, there's going to be situations where you're going to want very specialized functions. And this one's very specialized.
No, if you wanted it a half count for your clock, you could do a half, you could use that for a half count on the clock. It would be 2 on, 2 off, 2 on, 2 off, 2 on, 2 off.
Yeah, that's true. Okay, well. What else? Now, we have the other homework, don't we? Let's look at the other homework. We have a little bit of time left. Oh, actually, we don't really have any time left. We can finish that probably on Wednesday. We'll probably have time. We'll spend about 20 minutes going over homework, do a little lecture on Wednesday, give like 30 minutes for the quiz. That's all you guys need, about 30 minutes. So, I guess I'll see you guys on Wednesday.
On the 152, we need our flash drive.
Yeah, I would get your flash drives today.
Sure.
This was.
Oh, okay.
The continuing education now?
Oh, okay.
Yeah.
Okay.
I don't know.
And the one you missed, you're talking about, was that Friday? Okay. Yeah. Yeah, go ahead. It's likely.
It's not going to be exact.
There's gonna be like stuff on it.
Yeah.
It's going to be simple in all of them. If you get a chance to get one of these, that shows you all the homework. All the homework.
I don't think I have. Let's see. What you can do is just go to Moodle, and it's on Moodle.
It's on Moodle.
Mm-hmm. Yeah, it's. It's under assignments by topic at the very top.
I know I went on there like Friday afternoon, and there wasn't much on there. I saw there was something about some kind of homework, but I wasn't sure what it was.
Assignments by topic.
Okay. Thank you.
Yep. Oh, really? Hmm.
Last week, Monday, on Monday.
So, it's got me a little confused this time.
Mm-hmm.
So, what's the difference between, just a regular OR gate and the exclusive OR gate?
22?
Yeah, that's the one we just done, the last one.
Well, this one's a little bit different. This is a 3 input. Exclusive OR gate is Exclusive OR is.
Regular OR gates, 0, 1, 1, 1.
Yeah. Exclusive OR excludes the case where you have both ones.
So that's,
Yeah. A regular OR gate would have a 1 here. An exclusive OR has a 0. That's the difference between exclusive OR.
so if you got a 3 input, what would this, it'd still be the same? If you had one more?
Yeah, it's still going to be a difference comparator, even a 3 input. But you can't cascade exclusive OR gates like you do other gates. You can't go like this and then like that and get a 3 input. You can't get a 3 input exclusive OR gate by doing this.
See.
It's not going to give you the same thing. Which we'll talk about more later, but save the bulb. Oh man. Horse. Open example.
We didn't have any homework doing 152, right?
4 hours. 24 hours.
Just making sure, right?
Yeah.
I didn't think so.
Turn parts on off.
I still got to send that in. I think that was due Sunday. I think that has to be due Sunday too.
You guys heard that Cinder Septic or kids are coming in?
That's what I was going to do last time.
That was it. She was supposed to order the final ones on Friday.
Well, I got some confirmation email
Saying that it was ordered.
When? Today?
sometime. I think it was Saturday. It showed up
I didn't see it.
for the SimSoft stuff.
I'll have to check my Google. Is that board still in there?
What's that?
Still in the developer?
Oh. Yeah, probably.
Before I forget, I was supposed to have you sign this last week.
Mhm.
Forget to sign it. Be the second, third, and fourth.
$831.
That's because we're the company that I work for. They decided to move out of the United States.
I just did this yesterday.
The Federal Trade Act is making me do it.
Hmm?
They have to have a signature every day that they're here. They want the mileage stuff.
I mean, how bad is your program? You have to keep it, you've been continuously updated and having to fix it for the last 10 years.
I'm gonna check that board. This class 1 through 3.
Lab. You have a book for here.
I might like the lab notebook.
Oh,
Thing,
a little notebook for all the classes.
I wish
Yeah.
to put all the labs in it.
Well, all the classes have a separate book. Yeah.
Oh, okay.
Oh, let's see here. What is that? Let's see. No, that's not the right one.
What did you say?
Oh, we started already?